Okay, here's where we're going to show what AC circuits are on MultiSim, and this is basic RC with a resistor and a capacitor. And here's the AC source. You show it by the little squiggly sine wave. And they have capacitance reactance, which is just like resistance. And what happens is, for capacitive reactance, it always is pointing down relative to the resistance. So we have our resistance vector out here and our capacitance down here. The total impedance of the circuit is going to be Z, which is going to be the vector sum of these two, which is just the Pythagorean theorem. The actual reactance of the capacitor is 1 over 2 pi f. F is our frequency, and that's the capacitor value. And so it's a function of frequency. As x goes to infinity, or as frequency goes to 0, that value goes to infinity. So capacitors don't let anything through at DC. And what we are looking for in these circuits, or what the class looks for, is they want to know the relationship between the input signal and the output signal. So here the output signal is going to be across the resistor, so this is going to be the output signal. And then the input signal over here is going to be across this total impedance over here. So in this case, the output is going to be leading the input, and that's because the AC, the phasor rotation, is always counterclockwise in this direction for the little mouse indicator. So it's always going around this way. So if we're standing at any point, like right up here, we're going to see this output voltage before we see the source voltage, Vs. So that's what they call leading circuit. And we're going to set up an example and with MultiSim, and then you can see how to set up the oscilloscope. And that's the one big feature that you're going to need to use for AC circuits. So anyway, we do our standard place components. And for this, what we're going to do is we're going to start out with, we want our sources. And here we want the AC power source. And so it has a little squiggle line, and we say that's okay. We're going to put him down here. We're going to, well, we need a ground for our circuit, so we're just going to put him in the neighborhood. And now what we want to do is we want to go to our basics. And we're going to be in virtual rated, so we want a capacitor. There's a capacitor. We're going to say, okay, we'll need one of those. And now we're going to need a resistor, and we're going to put that guy down. And that's all we're going to use. And we're going to rotate this guy and move him a bit. And now we're going to put all our wires in here. And if this guy wants to cooperate, what we're going to do then is we're going to grab an oscilloscope from over here in our tools, and down here, and it'll tell us what it is. That's wattmeter. This is oscilloscope. So we go over here, we'll grab this guy, we'll move him here, and we're going to do that because we need to put both of these minus leads, we're going to hook those to ground point. Yep. And we'll try this again. We're going to hook this point into ground, and we'll connect that point to that point. Now this point we're going to look at, channel A is going to look at the input. So we'll do that. We'll kind of move him over, get him out of the way. Channel B is going to look at the output. So we're going to wrap him around to here. And so when we look at this on our oscilloscope, channel A is the source or the input, channel B is the output. Now for this, 120 volts is a little extreme, so we'll just knock them down to 20. And for this circuit, we'll change this guy. We'll make him 0.1. And we'll get this resistor value so we can see him. And we'll just make that a little bit bigger. So we'll make him 15. And that's what we have our circuit. So we're all ready to go. And now what we're going to do is we're going to run our program. And we're also going to pop up the oscilloscope. Now here's the oscilloscope, and it does take some practice to use these things. But basically what you want to do is you want to put in, this is triggering, and over here none, so it's just triggering all the time, which is kind of like what auto is. And normal it just triggers once, gets to the end, triggers again. And what we want is a single trigger. And that'll kind of give you a frozen picture of what it looks like. And what we can do is we can, well, we have to adjust some of our scales here so we can get them into a good scale. Now if we put them both at 10 volts, then we can see them both on here. And we're going to change the scale just a bit so we can widen it out. And what we can see over here, and if there's any doubt, we can say channel B is the output. So we're going to put this, well, we want to put them both on AC since we're looking at AC waveforms. And that really doesn't make a difference. But this higher value here is the input, and the output is the lower value here. If there's any question of which is which, you can just take one of it and we say B is the output, and we can hit it to 0 or ground and it goes away. So we know that this is the input. So if we get this guy back in the picture, we know that he's the output. And if we look at this, we can see time is moving from this side over here over to this side over here. So we can see that this point crosses the 0 threshold before this guy crosses that 0 threshold. This is the output and this is the input. So we say that the output is leading the input. Now, how much is it leading? Well, we have these time markers over here, T1 and T2, and we can move them slowly, and you can see this guy, this blue one is T1, and he starts moving around, and you can measure any point on the sine wave, and we might want to see where we get this guy almost to like 0 volts. And again, what we're measuring is 20 millivolts RMS, which the peak voltage is going to be higher. But that's about 0 volts there. And then we can take the T2 marker, and you can slowly move them with these arrow keys back and forth, or you can just grab them and quickly move them. So if we look at the next 0 crossing for this guy, it would be right about right there. And so that's 16.76. Now actually at 60 hertz it's going to be 16.667. So that's what 1 over 60 is. It's 16.667, and that's the period of the sine wave. Now if we want to know how much one leads the other one, we put this guy, put him on the nose of the smaller, the output. And sometimes you have to change time scales to get it really accurate. But right now we're just kind of doing it proportional. And that is about the beam, peak of the beam on this one, and that's about the peak of the beam on this one. And we say that the difference is 2.746 milliseconds. And the total period is again 16.667 milliseconds. So we divide that 2.746 by 16.667, and that gives us a number. It's basically 0.164. of a complete cycle. But now the complete cycle is 360 degrees. So we multiply that by 360 degrees, and the difference is going to be 59.31. So when they talk about phase shift or being out of phase, this curve here, the output, leads the input by 59.3 degrees. And that is a question that's going to run into all the time, and they're going to ask you whether the circuit is leading or lagging and what that value is. Now again, just the way this thing works, it's not that accurate, but you can get a good feel. Like, for instance, if you came up with numbers on a piece of paper and they said 63 degrees, and this is, 59, then you assume that you're correct. Now let's take a look if we stop it. And what we're going to do is get rid of this guy, and we're going to put an inductor in there. And let's see, we want inductor rated. Okay. Put him into the same circuit, and we only need one of them. And what we'll do is we're going to change his value. That thing, 1 millihenry, is a ridiculously small number. I don't know why they do that, but we'll do that, and we might just change this one to, we'll make them 5K, and we'll connect up the circuit. And all we want to do is, and I guess for this what we should be doing is we should show you the basics for the inductor. Again, this is just like the capacitor, only it has inductive reactance. Now this one, the capacitor was 1 over this type of formula, but this is just not 1 over. This is just the standard straight formula. So what this means is when the frequency is 0, with the capacitor it was infinite, but here when the frequency is 0, this has no effect at all. Now this one has the relation where this one, compared to the resistor value, this one leads by 90 degrees. So again, when we look at this circuit, and the capacitor was down here where the inductor is up here. So what we have with the same circuit with just replacing the capacitor with an inductor, now we have V out here and V in over here. Now when we make the vector thing, this V in, or the source voltage, is here, and V out is over here. So when we look at our vector rotation, again, we're standing, let's say, here, we'll see the input before the output. And that circuit is called a lagging circuit because the output lags behind the input. And let's see if the MultiSim is going to verify that for us. And so we've just changed the value from a capacitor to an inductor, and let's see what the output looks like. Okay, again, channel B, we're going to turn them off for a second. So the smaller one is channel B. I'm going to turn them back on. So this one is channel B, this one is channel A. And you can see on the timeline, this channel, the source, crosses before the output. So the output lags behind the input. And now we'll do the same thing with our markers to find out exactly how much it lags. So we're going to put this one guy right on the nose of the beam. And what we'll do here is we'll try to blow this one up, see if we can do better on how much. Okay, we're going to say that's the peak of that one, and right about there is the peak of that one. And the difference there, and this is the T2 minus T1. We say that's 1.932 milliseconds. And we have the same 60 hertz. So we're going to take that 1.932, we're going to divide it by 16.66, Then we're going and that turns out to be 0.116. Then we see if we can get the calculator in here, times 360, and that equals 41.75. So the difference, the phase shift between the input to the output is going to be 41.75 degrees. And in one case, we have the same circuit. When a capacitor is in here, the output leads the input. When we have the inductor in here, the output lags behind the input. So here's your output, here's your input. And so you're going to see that a lot too, whether it's leading and lagging, and again, what that phase shift is going to be. So that is the MultiSim demonstration with the oscilloscope. The oscilloscope's a really handy thing. You're going to probably use it a lot. And it's a really good verification tool when you're dealing with capacitors and inductors to, you know, again, get an idea or a feel for how the circuit works. And that's it for this demo.